Good day, everyone. Today we will discuss the comparative study of two unique underwater environmental seamount and coral reef using two innovative methods, environmental DNA or eDNA and Bay Remote Underwater Video Station or BRUVS. The study explored the ecological value of seamounts, focusing on whether they serve as biodiversity hotspots, biomass oases, or refuges for marine life. By understanding this role, we can better protect this vital ecosystem and address the challenge marine ecosystems face due to climate change and human activities. Seamount and coral reef are not only interesting from a scientific perspective but also crucial for maintaining global marine health. Understanding their unique contribution helps us prioritize conservation efforts in regions where resources may be limited but the stakes for biodiversity loss are high. To start, this research used eDNA and underwater camera to compare fish community in coral reef and seamount. Two environments that are distinct yet connected by their ecological function. Key findings suggest that while seamounts are not fish diversity hotspots, shallower seamounts act as biomass oases and refuges for threatened megafauna. This finding helps us understand where conservation resources might have the greatest impact in protecting marine biodiversity. Let's introduce the seamount. Seamounts are underwater mountains that rise at least 100 meters from the ocean floor. They can be divided into three categories. The one is hills. It is less than 500 meters tall. The two is knoll, which is between 500 meters and 1,000 meters tall. And the third is seamount, which is more than 1,000 meters tall. This submerged structure can create a highly productive environment by influencing ocean current and enhance nutrition availability. And seamounts are the least known ocean biome. As a result, seamounts are often considered to serve as biodiversity hotspots, biomass oases, and refuges for megafauna. Indeed, does real diversity compare to other ecosystems? Not quite really. However, despite their ecological importance, seamounts are under threat from activities like overfishing, destructive touring, and deep-sea mining. Understanding their role in marine ecosystems is crucial for developing strategy to protect them from irreversible damage occurred. The original concept of a biodiversity hotspot is defined as an area with at least 1,500 species, or 0.5% of global richness, under significant threat. In the marine realm, they continue the definition using the number of species, prospects of endemism, and global threats. Coral reefs are recognized as biodiversity hotspots. In contrast, seamounts have often been pursued hotspots due to their potential richness. However, this study questions whether their diversity is comparable to established ecosystems like coral reef. And the biomass. Biomass measures the abundance of mass of living organisms in a given area, providing an indicator of ecosystem health and productivity. And the key factor controlling the biomass, including temperature, nutrition availability, biodiversity, and human influence. An ecosystem with higher biomass then its surrounding is termed as an oasis. Definition of marine oasis and hotspot often mix and shift toward other work, like diversity oasis is a synonym of the hotspot, and biomass hotspot is a synonym of oasis. This study found that shallow seamount had much higher biomass and evaluated it as a potential biomass oasis rather than hotspot. Refuges are safe haven for species affected by large-scale disturbance such as climate change or human activity like overfishing. Seamounts are remote coral reefs can function as refuges by harboring high number of predators like sharks. Their remote location and challenging accessibility to reduce human exploitation, creating an economical barrier to harvesting. 好累哦。It's the primary object to determine whether seamounts qualify as biodiversity hotspot, biomass oasis, or refugees. Action. The study investigated which environmental conditions enhance biodiversity, biomass, and the abundance of threatened species across a broad ecological and anthropic gradient. The data for this study were collected through a series of comprehensive oceanographic campaigns carried out over several years. Altogether, a total of 224 BRUVS and 192 eDNA samples were collected across a wide range of environments. These environments were grouped into 5 distinct strata, each representing different ecological characteristics and depths. The first is a coral reef, which are a vibrant ecosystem, were sampled at an average depth of 13 meters. The second sample were gathered from shallow seamount at an average depth of 60 meters. The third continental slope are located at an average depth of 140 meters. The fourth sample were taken from intermediate deep seamount with the mid-depth average 265 meters. The deepest seamount sample with an average depth of 500 meters. And this is a figure the campaign was take place. Comparing shallow and deep environmental Comparing shallow and deep environment presents significant challenge due to the very nature of the sampling technique required. Coral reefs are typically surveyed by divers who directly observe and record marine life. In contrast, studying seamount fauna requires specialized methods such as environmental fishing, acoustic echo sounders, and remotely operated vehicles, or RV, due to the greater depth involved. To overcome this challenge and standardized data collection, this study employed 2 new methods, eDNA and BRUVS. Environmental DNA or eDNA is a cutting-edge method that involves filtered genetic material released by organisms into their surroundings. This approach is particularly effective for detecting cryptic, low-density, or elusive species that might otherwise go unnoticed. While eDNA excels in identifying species person, it does have limitations such as inability to provide data on the size of biomass of the organism detected. And the BRUVS is Bait Remote Underwater Video Station. It's an innovative tool designed to efficiently estimate species abundance and biomass in marine habitat. Each BRUVS setup includes Baletaud camera that attract marine life, allowing researchers to capture detailed footage for analysis. In this study, each deployment lasts 60 minutes, during which species were identified, counted, and measured using advanced video analyzing technique. To estimate biomass, researchers measure the lengths of up to 10 individuals per species from the BRUVS footage, then calculate the average. Missing data were addressed using advanced imputation algorithms, ensure robust and accurate results. And the eDNA sample were processed to identify species through the creation of molecular operational taxonomy unit, or MUTUs, which serve as proxy for species level identification. Then, following sequencing, processing, and cleaning to remove error and estimate the number of species. Potential eDNA contamination from BRUVS bait was also removed from DNA reads. This dual-method eDNA and BRUVS approach provide a comprehensive view of both species diversity and biomass across the study environments. This study examined 40 key environmental variables to understand their influence on biodiversity and biomass. These variables include physical factors such as temperature, chlorophyll, alpha, concentration, salinity, and depth, as well as human impact indicators like travel time to fishing market. By studying these variables, researchers gain insight into what drives marine life distribution and capture the complex interaction shaping marine ecosystems. Some environmental variables is following. The temperature affects the biodiversity across taxa, and the chlorophyll alpha indicate energy-rich area and shallow seamounts. Suspended particulate matter distinguish nutrition-rich and poor loam. Salinity differential water near the freshwater source, and the current influence species migration on seamount. The deep structure marine communities, and the human pressure impact diversity and biomass. The stratum may cover the rest of environmental variables. And how to modeling diversity and biomass. The author used the WEI-CHIEH regression trees, BRTS. It's a powerful statistical tool. We'll employ it to model the relationship between environmental variability and outcome, such as species richness and biomass. And the BRT BRTs excel in assessing non-linear relationship between the response and explanatory variable and complex interaction. They also evaluate the ability to manage complex interaction between variables. To ensure reliability, cross-validation techniques were used, and margin effects were analyzed to isolate the impact of individual variables on the observed patterns. And finally, 5 environmental strata are implied pairwise t-test. Let's look at the performance of the model. The study employed BRT model to analyze the data, and the results showed a strong model fit. For richness data, a CV score was 0.89 for species and 0.86 for motifs, indicating high reliability in predicting biodiversity pattern. In terms of biomass, the CV score was 0.73, which also demonstrated a good level of accuracy in model fish biomass trend across different environments. Let's see the result. The marginal effect found that species richness consistently decreased with increasing depths, and the trend was also particularly sharp for mutos. Through the rarefaction curve, it confirmed higher biodiversity level on coral reef compared to other environments, emphasizing their role as biodiversity hotspot. Deep emerged as a most significant factor driving richness, followed by habitat diversity, which was positively correlated with species richness. And the left figure was the species richness by BRUVS, and the right figure is a muto richness driven by eDNA. And the result of biomass. Fish biomass displayed a dome-shaped pattern, peaking at intermediate depths. This trend was consistent for large predator and shark, whose biomass mirrored the overall pattern. The shallow seamount in particular show nearly 3 times the biomass of coral reef. And the variable importance for biomass. The depth was the most influential variable affecting biomass, followed by habitat diversity, which account for 23.6% of the variation, and the travel time to market, which contribute 11.7%. And the last result, assemblage structure. The study identified distinct fish assemblage across the 5 environments. Coral reef and deep seamounts hosted distinct fish community, with coral reef exhibiting 84% unique mutos. Interestingly, species share between coral reef and seamount were predominantly large predators, underscoring the role of seamounts as refugees from anthropogenic pressure in shallow water. For the discussion, the findings reinforce the classification of coral reefs as biodiversity hotspots with significantly higher species richness compared to deeper environments. In contrast, seamounts were not biodiversity hotspots, but demonstrated their value as a biomass oasis. Shallow seamounts in particular host nearly 3 times the fish biomass of coral reef. The study suggests that mobile large predators may use shallow seamounts as refuges to escape anthropogenic pressure on coral reef. This finding underlines the importance of conserved shallow seamounts and continental slopes, especially given their role in supporting threatened species like sharks. And the first point of conclusion is biodiversity distribution. To understanding the spatial distribution of biodiversity is crucial for addressing ecosystem change caused by climate change and human activity. And this study highlights the varying ecological role of coral reef and seamount, emphasizing the need to approach conversation with this difference in mind. And the second point is conservation priorities. Shallow seamount and continental slope, which support high fish biomass and large predators, should be prioritized for protection. And these areas are currently underrepresented in global conservation efforts, despite their ecological significance. The third is the future research. Advanced technology like eDNA, metabarcoding, and broaden the scope of biodiversity study. This will enable more refined conservation strategy and improve our understanding of the ecological dynamic in marine environment. And this is my report. Thank you for your attention. I will